A coffee mug and a torus, or donut shape, are mathematically identical structures. This identity is established by homeomorphism, a core concept in topology that completely ignores metric properties like distance, volume, or curvature. Topology studies properties preserved under continuous deformation, meaning stretching, bending, or twisting are allowed, but tearing or gluing parts together are strictly forbidden. Imagine the mug made of soft clay. The handle provides the single hole. If we continuously shrink the cup part and expand the handle, we arrive at the torus shape. The crucial feature preserved throughout this deformation is the genus, the number of holes. Both the mug and the donut possess a genus of exactly 1, confirming their topological equivalence and establishing the foundation for classifying the qualitative structure of spaces. Homeomorphism is formally defined as a specific type of function, a bijection between two topological spaces x and y. For the spaces to be homeomorphic, two conditions must be met. The function f mapping x to y must be continuous, and its inverse function, f inverse, mapping y back to x must also be continuous. Continuity ensures that points arbitrarily close together in x map to points arbitrarily close together in y, and vice versa. This guarantees the transformation is smooth and reversible without introducing breaks or merging distinct points. If such a homeomorphism exists, the spaces x and y are topologically equivalent, denoted x is equivalent to y. This relationship satisfies reflexivity, symmetry, and transitivity, confirming its utility as a robust classification tool.
To prove two spaces are not homeomorphic, topologists rely on topological invariants. These are properties of a space that remain absolutely unchanged under any continuous deformation. Primary invariants include connectedness, compactness, and dimension. For example, a line segment is connected, but if we remove a single interior point, it becomes disconnected. If space X is connected and space Y is inherently disconnected, they cannot be homeomorphic. Compactness relates to covering a space with open sets. A closed interval is compact, while an open interval is not. Dimension is also invariant. A curve, being one-dimensional, can never be homeomorphic to a surface, which is two-dimensional. The most intuitive invariant for classifying surfaces is the genus, defined as the maximum number of non-intersecting closed loops that can be cut from the surface without disconnecting it. A sphere has genus 0, as any single loop cut will divide the surface into two pieces. The torus, or donut, has genus 1, corresponding to its single hole. The coffee cup handle provides the single loop necessary to confirm its genus of 1. Since genus is preserved under homeomorphism, any two surfaces with different genera, such as a sphere and a torus, are fundamentally distinct in topology. This invariant allows for the complete classification of all orientable closed surfaces based solely on their number of holes. Visualizing the cup to donut transformation requires focusing on the continuous movement of material. Start with the mug. The handle forms the fixed loop defining the genus. Gradually, the main cylindrical body of the cup is continuously shrunk down towards the handle, while the handle itself maintains its relative size. The bottom of the cup and the rim are compressed until they meet the central axis defined by the handle's loop. The resulting shape is a perfect torus. Crucially, no points were torn apart, and no new points were suddenly joined during this process. This continuous transformation demonstrates the existence of the required continuous bijection and its continuous inverse, satisfying the formal definition of homeomorphism.
Consider the difference between a circle and a line segment. If we remove one point from the circle, it remains connected. If we remove one interior point from the line segment, it immediately becomes two disconnected segments. Since the property of remaining connected upon point removal differs, the circle and the line segment are not homeomorphic. Another key distinction is between the Mobius strip and the cylinder. The Mobius strip is non-orientable, meaning a normal vector cannot be consistently defined across the entire surface. The cylinder is orientable. Orientability is a topological invariant, proving these two surfaces are fundamentally distinct, despite both being surfaces with boundaries. Topology is highly practical, driving the field of topological data analysis, or TDA. TDA uses persistent homology to find the underlying shape or topology of high-dimensional datasets. Data points often cluster in complex manifolds. Persistent homology tracks topological features, such as holes or voids, as the data is filtered at varying scales. Features that persist across many scales are considered statistically significant, revealing the intrinsic structure of the data. This technique is used extensively in areas like image recognition, material science, and analyzing complex biological networks, providing robust structural insights independent of specific coordinate systems or noise. In physics, Topological Quantum Field Theory, or TQFT, studies quantum field theories whose properties depend only on the topology of the spacetime manifold, not on its geometry. TQFTs are crucial for understanding exotic states of matter, particularly in condensed matter physics. They predict the existence of topological order, where the ground state degeneracy of the system depends directly on the genus of the surface the system resides on. This concept is foundational for developing fault-tolerant quantum computing, where information is encoded in non-local topological properties, making it inherently immune to small local environmental perturbations or errors.
The equivalence between the coffee cup and the donut hinges entirely on the preservation of the single whole, the genus 1 invariant. Topology successfully abstracts away specific physical dimensions and focuses solely on connectivity and continuity. This qualitative approach allows mathematicians and physicists to classify spaces based on fundamental structural properties rather than arbitrary measurements. Homeomorphism provides the rigorous mathematical framework for this classification, proving that under the lens of topology, the rigid ceramic mug and the soft, doughy torus are indeed structurally indistinguishable.